of maybe intersection of two functions, say y1, f1 of x, and y2, f2x. So you want to find moment of inertia of this area with respect to x and y. And the second case, obviously, are the composite areas. Okay? So just very quickly, I'm going to maybe do a quick problem here to finish that discussion. Let's say you want to find the moment of inertia of a shape like this. One of the problems in the book, it's actually the case. Okay, something like this. This is y of k, x is 1 cubed. This is a, and this is b. Let's say you want to find a moment of inertia like this. So in your classes, I've already done a problem, and honestly, that's not really the important type of problems that we're dealing with in engineering. I would just go over the general concept. For I of x, right, you need to evaluate this integral, which is y squared dA, and for I sub y, you need to evaluate x squared dA. So it all comes down just to defining or setting up dA and performing these two integrations. For I of x, okay, you do a dA which is parallel to the x-axis. Okay, so this would be dy, and dx would be, the width would be what? In this case, this is constant, so it would be, let's say, I call this x1 minus x2. So in this case, you have just x1 minus x2 times dy. For case of I sub y, you set up dA with sides parallel to y-axis. So this is going to be dx, and this is y2. In this case, y1 is 0. So it's an easy case. But if you had another function like this, it would be y2 minus y1. But anyway, I just wanted to quickly do a simple problem. So you set this up. So in this case, it would be y2 minus y1. In this case, y1 is 0 times dx. So all you need to do is just set up those integrals. For I of x, you just have integral of y squared dA, or y squared times x1 minus x2 dy. So you just substitute for x1 and x2 in terms of y as a function, express them as a function of y, right? So here, you have what? You have x1, of course, is constant. So in this case, dA would be a minus x2. x2 is from this function, so you need to find x in terms of y. So you just raise both sides to the power of, well, that's actually 1/3 or 1/3. Yeah, that's what I thought. Okay. So you have y cubed is k cubed times x. So you find x is equal to y to 3 divided by x. Okay. And of course, you can't find k, given that you have the coordinates of this point, which is a, and b. If you substitute that there, you have b is equal to k A 1/3, so K would be B over A to the 1/3. So anyway, you have x1, which is A, minus x2, which you now found it, okay, divided by k3, so we have, here you have, divided by that, over b times a to the 1/3. Okay, that's x1 minus x2 times y1, y squared dy. Simplify that, okay, you get then the integral, and dy changes from 0 all the way to b, so that's the bound of integral, right? So you will have, multiply these, you have a y squared minus y5 divided by b times a to the 1/3 dy, perform the integration, so you have a over 3y, 3 minus 1 over 6, b, okay, y6, a 1/3 going from 0 to b, okay, and you have what? You have a over 3b, 3 minus, that would be d6, d5, so you have a 1/3, b5, and so on, okay? So basically you find that, right? And I did another example, I hope I didn't do it too quickly, because that should not come out so like that. It doesn't look right, especially the order, it shouldn't come like that. But anyway, that's basically it. The key is to set up these differential areas, okay? And I did another problem. The question is, are you really encountered these kind of problems? Honestly, hardly, if ever. So the more important case is the composite area. So that's what I'm going to focus on, okay? So let's focus on that, because I think I started that, but we didn't finish. So let me erase all these and go to that one. Okay, so composite shapes. With composite shapes, there are a few things that you need to know. First of all, like centroid, the moment of inertia of simple geometric shape are tabulated in a table given in the back of your book. For a rectangle, a triangle, circle, half a circle, and so on. If you look at that table, those values are given either with respect, either with respect to the centroidal axis of those shapes, or an axis parallel to the centroidal axis. And I'll talk about that. So that's the first thing you need to know as far as the composite shapes, how to use that table. Second, you remember centroidal axis. What is the centroidal axis? You have an area, you locate the centroid, the axes that go through that, the x and y coordinates set at that centroid are called centroidal axes. You don't get to see the significance of the centroidal axis in this course, but they're very important in the next course. Because as you will see, for instance, if a structure, if a beam is bent about the centroidal axis, which normally coincides with the neutral axis, every layer of the beam goes through some deformation, but those layers that are along the central axis do not change shape, length. Of course, these are all foreign to you. We'll get to see that in the next course. This whole subject of moment of inertia has nothing to do with statics. You just learn it for the next course. But the point is that centroidal axes are important. Another concept is that something that you need to remember is the parallel axis theorem. You remember parallel axis theorem? How many of you remember that? What it was? From calculus. So, okay.
Not from calculus, from physics.
Right, calculus, physics, whatever, right? This is what it was. If you have a moment of area of a shape about an axis, let's say AD, which usually use this notation. So if you can find the moment of inertia of this area about an axis, and then you're asked to find the moment of inertia of the same area about an axis that is parallel to this, and you have the vertical distance between the two, you don't have to recalculate that. You can just simply find the moment of inertia about this new axis by writing the moment of inertia that you had calculated about the old axis and add to that the area times the distance squared between the two. This was called parallel axis theorem. These are two things that you really need to know before we go into composite areas and how you find the moment of inertia of those shapes. Also, these formulas are not really that difficult to derive if you want to. You don't have to, but let me at least derive one of them to show you both of these, right? Let's say you want to find moment of inertia of a rectangle with a width b and height h. First, let's find the moment of inertia of this shape about its centroidal axes. These are the axes that go through the centroid of this shape. How do you do that? I of x is y squared dA, right? So for that one, we said you set up a dA with sides parallel to the x-axis. So this is the dA. This would be then dy. This is dA in this case. So dA would be simply b times dy. In order to perform this integration, this shape is symmetric with respect to this axis. So instead of performing this integration from here to here, I do it from 0 to here, or to h over 2. Or in other words, I write Ix is 2 times 0 to h over 2 of y squared times dA, which is b dy, or would be 2b 0 h over 2 of y squared dy, or 2b times 1/3 y cubed from 0 to h over 2. If you simplify this, you will see that you get 112 b h cubed. Okay? You can do the same thing to find the moment of inertia about centroidal y-axis. And that would be what? Iy would be the integral of x squared dA. And dA in this case is this. Or in other words, this is dx. And this height is constant, so dA would be simply h times dx. And again, since this is symmetric with respect to this axis, I just do the integral from here to here and multiply that by 2. So that would be twice the integral of x squared times h dx, going from 0 to b over 2, or 2h 0 b over 2 x squared dx, or 2h 1/3 x cubed 0 to b over 2. You'll see you get 1 over 12 h b cubed. So if now you want to find the centroid moment of inertia of the same shape about, for instance, this axis, x, which you see is tabulated in the book as I of x, is bh cubed over 3. The way they find it is you already have the moment of inertia on the x-axis. So I of x would be 3h cubed over 12, which is the moment of inertia about this axis, plus the area of this rectangle, which is b times h, times the square of the vertical distance between these two, which is h over 2. So h over 2 squared, which will give you that, bh cubed over 3. That's how you do it. So these two pieces of knowledge are really the key to do composite shapes. So with that said, let me demonstrate the concept through an example. Any questions? Any questions? Yes?
I'm sorry, where did you get bh times h over 2 squared?
Oh, you know what? You just noticed it. That should be h. Yeah, that's right. And that's bh cubed over 3. Where I got that?
Yeah, no, just the second term, yeah.
This one?
Just, yeah.
Yeah, let me show you. Maybe I did it too quick. We have the, this is this rectangle, right? I have the moment of inertia on this axis, right? And that we found to be 112 bh cubed.
Yeah.
Now I want to find moment of inertia on this axis. And as I said, moment of inertia on x is the moment of inertia on x bar plus the area times the distance squared. This is the distance squared, which is h over 2.
Okay, perfect, thank you.
Okay, any other questions? Yes?
So your original line is you're taking from the x bar and you're going down to the x?
Yeah, any axis that is parallel to it, as long as you have the vertical distance between the two. That's parallel axis theory. Okay. Okay, so let me do a good problem. Problems in the book are just too simple. I don't know why in the composite shapes, book does not have a good problem. They're only made maybe of 2 pieces or something like that. So I just thought to do something that will really give you a good understanding or appreciation of the concept. Okay? So this is the problem I'm going to do. Let's see. Let's say you have a shape like this. 20 meters here, 20 meters here. Okay. You cut out a piece from this 5 meter by 5 meter. You cut out another piece, a triangular shape. This is 5 meters. This is 10 meters. And then another piece here, a half a circle with a radius of 2 meters. And you're going to find the moment of inertia of this shape. Okay? In moment of inertia problems, the composite shapes, there are two cases, or two types. Type 1, which is mostly the kind of problem that book gives you, is you're asked to find a moment of inertia about a given set of axes. The second type of problems is you're asked to find a moment of inertia about the centroidal axis. This is, of course, more work, but is more important because, as I said, you study moment of inertia because what you really need in the next course is how to find the moment of inertia about the centroidal axis of the cross section. Okay? Not to scare you too much, the cross section that you'll be dealing with, though, in the next course would be very easy. Either it's just a triangle or a rectangle or a bunch of rectangles. That's most of the structural shapes are like that. But anyway, so I'm going to do this problem because it's inclusive. In order to do this, you have to do this. Okay? So this is what I mean. So you're given this shape. First, you need to find the centroid of this shape, right? And once you find the centroid, set up a coordinate system along those centroidal axes, and then find a moment of inertia about that. So, step 1 is what? Very similar to centroid. You need to divide this area into sub-areas, AIs. Okay? So that's what I do. This is what I'm going to do. So I consider this as A1, which obviously is negative. So it's basically areas pi r squared over 2, right? Let's consider this as A2 is also negative, and this as A3 also negative, and A4 is this area. That's step number 1. And step 2, you set up a table. To save time, I set it up from the previous class. So, since you need to find the centroid, you need to perform basically the same operation here. So let's do that. You need to find the centroid of this shape. You need to have the centroid of each sub area, right? So you know, for instance, here, this is what? This was 3 or 4 pi over 3, 4r over 3 pi, right? So the centroid, you find the centroid of each of these, right? And you find, with respect to y, these x1 bar, x2 bar, x3 bar, and for this shape would be simply here, x4 bar, right? So you just calculate them. I have the results here. So for the first one is, of course, once you calculate this, subtract it from 20, and so on, you get, well, you need to first calculate the areas, 6.28. This is 25 negative. This one is also 25 for that rectangle, and the large area is 400. So this area, this area, this area, and then the square. So those are the values. So you add those up, you have the total area, which is sigma AI, and that will be giving you 343.7, given that those are negative. So you locate the xi's, and I will tabulate them here, 18.85, 3.33, 437, I'm sorry, 17.5, 17.5, and this one is 10. Basically, as I showed here, x1, x2, because this is 10 divided by 3. This is like 1/3 of the distance from here, 1/3 here. So this is 3.33. This is 1.67. And this is roughly, I mean, would be what? 8 divided by 3 times 3.13, roughly about 0.85. Okay, so that's how I come up with those numbers. So multiply these, XIAI, you have 118, 4 negative, 83.25, that would be also negative, 437.5 negative, and then this guy would be 4,000. So you add those up, you get summation of AI, XI, and that will be 3361. So you divide this by that, that will give you the X bar for the shape, that comes up to be 9.8 meter. In other words, the Y centroidal axis would be somewhere here. This distance, X bar, is 9.8 meters. Okay? So this is Y. To find X centroidal axis, you need to evaluate these. So Y bar for each shape. This is Y1, this is Y2, so this is Y2, this is Y1, this is Y3, and this is Y4. So you just tabulate those. So if you do that, you get 10, 11.67, 17.5, and 10. Multiply that by the corresponding areas, you get 63 negative, 291.8 negative, 437.5, and 4,000. So you add those up, that'll give you summation of AI, YI, and you get 3207.8. So you divide this by that, will give you Y bar for the shape, that comes out at 9.3. That means the X centroidal axis would be located at, this is Y bar, 9.3 meters. So you set up the coordinate axis, going through the centroid. Now you want to find the moment of inertia of this shape about those axes. And now that parallel axis theorem and this table as the tools that you need come to your help. Step by step is as follows. You find the moment of inertia of each shape, following the formulas in this table, about its own centroidal axis. Say you have this shape, you have this shape, you have this square, and then this large square, right? Each of them have these centroidal axes of their own. Okay, so you find the moment of inertia of each shape first about their x centroidal axis. And that's what this column is. So let's start with this guy, A1. You go to that table, you see that this moment of inertia of that shape with respect to its x axis is listed as 1/8 of pi r to the 4. So it's 1/8 pi 2 to the 4. And of course, negative. So you calculate that. It would be 6.3 with respect to this axis. You go to the same table, you want to find the moment of inertia of this shape about this axis. You see for any triangle with a base B, height h, moment of inertia about this is 136 bh². If you want to find about this axis, this becomes B, this becomes h. Okay? So B is 10, h is 5, so you have 1/36, B 10, h is 5, so that will give you 11.67 negative. Okay? Oops, I'm sorry, 29. What am I doing here? Oh, 34. 34. Okay, 34.7. You go to the next one. That square is 112 bh². If this is B, this is A, about this is 112 bh². So it's 112. B and H in this case happen to be the same. So that will give you, okay, 52.1. Remember, like those areas in centroid, when you don't have an area, its moment of inertia is also negative. Then the large one is a square, 112, 20, 20 cube. If you calculate that, results would be 13,333. But that's not what you need. You need the moment of inertia of each of those shapes about this axis, not their own centroidal axis. So what you calculated there, you need to add this area times this distance squared. What is that area, that distance? This is 9.3, this was 10, so this is 10 minus 9.3, so it's 0.7. So for the first one, you just simply write 6.3 plus the area, which you have here, 6.28 times the distance squared. And that will give you that value. That will be 9.4. Do the same for that triangle. You have the moment of inertia about this axis, which is this axis. Okay? But you want that about this axis. What is the distance here? This was 11.67. This is 9.3. So this is 11.67 minus 9.3. So that would be 2.37 and 2.4. So you just simply write what you have here, 34.7 plus the area, which is 25 times 2.4 squared, which will give you 174.3. Okay, you're going to the next one. You have the moment of inertia of this shape about its centroidal axis, but you want that about this axis. This was 17.5, this is 9.3, so this distance, which is what you need, is 17.5 minus 9.3, or 8.2. So you just write 52.1 plus the area, 25, times its distance, 8.2 squared, and that will give you, okay, 1,733.1. Same thing about the last one. You have the moment of inertia about its own centroid, which is 13,333, okay, plus its area, which is 400 times the distance between its centroidal axis and this axis, which is 10 minus 9.3, or 0.7. So it would be times 0.7 squared. That will give you, check, 13,000, okay, 333, and I don't have that exact value, but anyway. So all you need to do now, just add these up, and that's what you were looking for. So if you add these up, it will give you 11,612.5 meters to the 4. So moment of inertia on the shape about an axis is the sum of the moment of inertia of the sub-areas about that axis, and that's what we did. Are we done? No, it's just half of what you need to do, right? We still have to find the moment of inertia about y centroidal axis. So you have to repeat this for I about centroidal axis y of each shape. So you need to tabulate all of these. And that means you need to find the moment of inertia of this shape about this axis now. This one, and this one. Okay? So you go to the tables again and tabulate all of these. After you've tabulated those, right, which I'll give it to you here, 6.3, okay? This one, 138.9, 52.1, and this comes out to be the same, 13,333. Once you tabulate those, now you need to find the moment of inertia of each shape about the central axis y of that whole shape, which is this plus ai and d prime I squared. That is the distance now from, say, here to here, from here to here, from here to here, and from here to here. Those are the distances between the two parallel axes. So you write all those down, add them up, and that will give you the moment of inertia about the y-axis. Do you want me to write these down? It's good to have them if you want to repeat them. 520.65 negative. This is 1182.2. This will be 1534.4. This comes out to be 13,347.3. If you add these up, you get 10,112.13 meter to the forward. That's the moment of inertia of that shape about the y centroidal axis, right? So you need to hire an accountant to take care of all these for you. Of course, I would be lying to you if I tell you you get something like this in the exam, because it's going to take an hour to finish a problem just like that, right? Yes.
So does it matter how, like, if the distance is positive or negative from the centroidal axis?
Good question. You know, the way you set it up, oh, I see what you mean. I see what you mean. Versus here, no, because the distance in this case doesn't matter, because the distance is always squared.
Mm-hmm.
So you don't care. Even if it is negative, doesn't matter. That's why always have that parallel axis theorem. Remember, cross the area times the distance is squared. So that positive, or that summation is always a summation, not a subtraction. Any other questions? Enjoy your long weekend. Some of you asked me to send an article that I mentioned in another class. So I sent it all to you. Timing is perfect. Read it.